right, good afternoon. Good morning. Good, whatever it is.
Almost noon.
Almost noon. All right, any questions before we jump into stuff? So let's talk about recursion a little more. So we're doing recursive functions for tree manipulation and searching and adding and stuff like that. Chances are that if this is the first time you've encountered recursion, you may still be kind of trying to make perfect sense out of it. And our tree code is fairly complex. There's dynamic memory and stuff like that. So let me show you an example of a simpler recursive function. You can make these things up yourself, but just as a exercise for thinking about, let's make a function for computing factorials. Okay, so n factorial is just 1 times 2 times 3 all the way up to n. And we know we can do this with a loop, right? So we could make a for loop and we could have a running product that's equal to 1 and keep multiplying by n and so on. But we can also do this recursively. So let's make a factorial function and let's use it to calculate 10 factorial, which is something with a 5 and some zeros at the end. And we can use a fact that you know we've bumped into in 215 in some inductive proofs, which is n factorial is the same thing as n times n minus 1 factorial. Because this says multiply all the numbers from 1 up to n minus 1. And if we multiply all the numbers from 1 up to n minus 1 and then multiply by n, that's exactly the same thing as multiplying all the numbers from 1 up to n. So this is a recursive way to think about factorials, and we can code that like so. To find n factorial, let's just calculate n minus 1 factorial, multiply by n, there's our answer. And so this is a simpler function to contemplate than some of the stuff we've been writing for binary search trees. And if I run this exactly as it is, it will blow up, and it might even crash my machine. Because this is what we call infinite recursion. To calculate 10 factorial, I'm going to need to call fact with an argument of 9. And to calculate 9 factorial, I'm going to have to call with an argument of 8. And yes, so it needs to stop at a base case at a value of 1, for example. So we know what 1 factorial is. 1 factorial is just 1. So I can fix this by saying if n equals 1, return 1. That's the base case. But if n is not equal to 1, what is n factorial? Well, I don't know, but it's n times n minus 1 factorial. Did I forget standard I/O, man? Alright, so if we run that, and it starts with a 3 and a couple of zeros at the end. But anyway, that's 10 factorial. Right? So this is something you can mess around with if you want to dig deeper into recursion and actually think about how your call stack behaves as you make further and further calls. What's kind of weird about this, to some ways of thinking, is the only time I actually return a number is right here. I return a 1. But I return other things, but they're always, the result of some sort of algebraic expression involving a call to this function. But the only number that I actually return is 1. Well, I can do longer ints, but I won't get a very meaningful answer because, ints overflow at 2 billion something. Oh, okay. Well, but anyway, it's an interesting thing to try in here. But if I tried this with some number like a billion, right, then there's a good chance I'll overflow my stack and I'll crash my machine. All right, let's see. So chat question, I have a problem. scanf input d%d at A at B. When entered a number more than 100,000, number B will only be the first digit of the entered second number. So if you're declaring A and B to both be integers, they should go up to about 2 billion. And I saw you popped into office hours waiting room for a few minutes this morning, but I wasn't able to get to you before you had to leave. But you can definitely pop into office hours tomorrow. I assume that's a typo on the first D. Yeah, the only thing I could think is if A and B are not declared as integers, if they're characters or something, then you'll have problems. And input needs to be long enough to store, both strings, both numbers as strings. So make your input something big, and maybe try printing out your input before you scanf, and see if input's getting truncated somewhere also. Yeah, try those things and shoot a note or come by office if that doesn't resolve it. Is there a technique to spot recursion when solving problems, something that immediately stands out in problem solving? I don't know. Like I say, sometimes you get in a mode where you start doing a lot of recursion and you can start to see the whole world recursively. There's certainly a lot of problems that can be phrased as a recursive algorithm. They're not always good problems to solve recursively, but the opportunity is always seems to be there. But I don't know of a particular technique to identify a recursive path to a general problem. But start thinking about other problems in these terms, and you can find a lot of applications, right? How do you watch a 10-hour movie? Well, watch the first 5 seconds, get a friend to watch the other, 9 hours, 59 minutes, 55 seconds, and tell you what you missed, and then put that together with the 10 seconds you watched, and there you go. Right? And if your friend is yourself, then all you have to do is have a 5 or 10 second attention span. That's a weird example. All right, so play around with recursion. There was a question in the earlier section. Yeah, exactly. There's a question in the earlier section about using fopen and how to read from a file, and most of the students I've been talking to in office seem to have that part working. But I posted some code on the sample code area. It's called go2, very undescriptive name, but it just shows you some of the basic operations, right? Basically, if you want to do file IO. Make a pointer to an uppercase file. That's the thing that you use to read from or write to files. And it stands in the place of standard in or standard out in other function calls. So make a file star fp is the typical name for file pointer, and assign that the return value from fopen. And our goal is to get down here to fgets. Normally we say fgets character array length comma standard in. We can put in a file pointer here instead of standard in, and then fgets will read from a file instead of reading from standard in. So this is all trying to set up this file pointer. So declare it to be a uppercase file star, and then assign it a value from fopen. So fopen takes two arguments: the name of the file you want to open. This can be something like this in your local directory, or it could start with a slash if you want to put in a full path. And then an argument in double quotes that says, how do you want to open the file? Do you want to read? Do you want to write? Do you want to append? Things like that. If we're reading, which is what we do in PA2, this is just double quote R. And that returns a pointer to a structure that can be used as an argument for fgets. And before you use it, double check, make sure that pointer is not null. If anything goes wrong in opening your file, FP will come back null. So you can check that with FFP equals null and detect database errors. File doesn't exist or you don't have permission to read it. Otherwise, at this point, FP can be used anywhere that you would use standard in particular inside fgets. So you can call fgets character array length comma FP, and instead of reading from standard in, it will read from the file that we opened up here. And it will read until it either finds 119 characters, or it hits a new line, or it hits the end of the file. So you make your buffer big enough to hold an entire line, but typically it will read up to a new line, and then fgets will come back. And it will load this character array with the characters it read from the file, up to and including the new line, and it will throw a null terminator on the end, which is why this can only hold 119 characters, because it needs that 120th spot for the null terminator. And it will return a flag, fgets will. And if you try to read past the end of the file, fgets will return null. And that's your hint that you've hit the end of the file, and so you can kick out of your while loop. So typically we iterate with something like while fgets does not return null, and then in here you can do whatever you want with the line that you read. For example, break it into a plate, first name, last name, load it into your tree. All right, any worries around that? Alright, so that's the deal with file pointers and fopen and fgets and all of that. Alright, let me mention a few more details / issues around PA4, and I'm seeing these coming up. These are gotchas that will kind of naturally occur in an assignment like this. So you're building a binary search tree, right? So inside main, you have a root. And to initialize our tree, instead of calling an init function like we did with lists, we want to initialize just by saying root equals null. That should be your empty tree. And there's no reason to call malloc inside main. You only want to call malloc if you're creating a node. So if you said root equal to malloc and then said root equal to null, all you've done is made a memory leak, right? Unless you free the node that you malloced, in which case you just spent some CPU time allocating memory and then freeing it. So really the empty tree, we just say root equals null, and that makes the empty tree. So that's one thing. Next thing, when you want to add, you call your add function, you pass the root to it, and the license plate, the names, or whatever. But make sure that your add function is returning the root of a tree and that you're setting root equal to that return value. If you just call add, your root's always going to be null, and that leads people to start setting root equal to malloc, and now you're fixing a bug by introducing another bug. So have add return the root of a tree and set root equal to the return value from add. Alright, in your add function, it's mostly recursive, right? So use string compare to decide where to add. And get extra friendly with the manual pages, right? So look at the manual page for string compare. It takes two strings, S1 and S2, and it tells you, it compares those two strings and it returns an integer less than, equal to, or greater than 0 if S1 is respectively less than, equal to, or greater than S2. So the key for our binary search tree is license plate. And so we want to compare the license plate you're adding with the license plate at the root of the tree. And you want to do that using string compare. And if, for example, you decide that you should add to the left, what you want to do is set your root node's left child to be the result of calling the add function on that left subtree. And then when you're done, return root. Why do things take a constant char star? I've never used the keyword constant in C, so I don't think it's necessary. But you see it sometimes, and it means things to the compiler. It's used when you want to indicate that this pointer is not going to change, I believe. But I don't know what it does internally in the mind of the compiler. But I don't think you need to use that keyword. You mentioned pointers. Do you want us to use pointers for the line parsing as well, or just the binary search tree code? I'm not worried about how you implement the parsing. Whatever will make it work, I'm fine with. Yeah. All right. So if you're writing your add function, right? Remember, it returns a struct node pointer. And use string compare to see if you should add to the left or the right, and to add to the left or the right, call the add function on the left or right subtree, add your data, but then set the left or right subtree of your root to the return from add, right? That's doing the same thing as in main when you say root equals add. It gets you from the case of an empty tree to a non-empty tree. The other issue is when the root is null. So this is still the add function. And you call add on a tree, and that tree is empty. Okay, this is where you need to create a new node. So new node equals malloc. And you want the size of whatever your structure is, a struct node. Okay, that creates a block of memory and makes new node point to it. What is in this block of memory, though, is a bunch of pointers. There's a plate, there's a first name, there's a last name, there's a left, and there's a right. So your new node is probably 40 bytes, because pointers take 8 bytes typically. There's not enough space in this node to store somebody's first name and last name and 30-digit license plate, right? All you have is pointers to memory. But we can change those pointers to point somewhere that has the person's first name and last name and so on and so forth. So suppose we're adding, plate, first name, last name. Okay, here's what you don't want to do. If I say new node arrow plate equals plate, what's going to happen? This piece of my new node, this pointer, is going to point right there. It's going to point to the variable that was passed from my main program, which probably came from a scanf. Which means in my main program, the next time I change that variable, this is going to change. It's pointing to the same place, right? Plate, but the thing at that place will change because that's a local variable inside main. And so if you're finding that your license plate data is changing, or you find that every node in your binary search tree has the same plate, first name and last name, there's a good chance you're doing something like this. You're copying pointers, not the things pointed to. This is really subtle, but this will come up again and again. It will come up in 223 in Java when we're dealing with objects. There's a difference, subtle but profound, between the pointer and the thing that it points to. So this is just copying the pointer. It's saying I want this node's plate field to point to wherever this variable is pointing. Okay, so don't do that. What you want to do is find a new spot in memory. How do you do that? By calling malloc. So how much space should we malloc? Well, we need enough space to store the contents of this string. Well, how big is the contents? There's only one way to know. It's not size of, it's string length. Size of will return 8 because plate is a pointer. Pointers take 8 bytes. But if I use string length, that's a function that will go through here and look for a null terminator. So I can say string length of plate. That's how many characters are in that plate. And then I'm going to add 1 because I actually need to also store a null terminator at the end. So now new node arrow plate is not pointing up here. It's pointing somewhere else in memory where I've set aside enough space to store my license plate plus a null terminator. And now we can do string copy. And again, look at your manual pages. Right, so string copy is one of the weird arguments where the destination comes first. It copies from the second argument to the first argument. There's a constant there. I don't know why. Copies from the second argument to the first argument. So string copy into new node arrow plate, comma, plate. So this will read the stuff in memory that this argument is pointing to and copy each character into these locations. After that, when main runs again and it changes the stuff that this is pointing to, this stuff is preserved. It's a new copy, right? And it will be perfectly stable until your code changes it. And so do the same for first name and the same for last name, and then you're good to go. And since this is part of the add function, when you're all done with this, return new node, because that's the new root of the tree. So when we go to free the node from memory, we have to free the memory for the plate first, last, and then the node itself. Yes, so freeing is a little more complex. When I'm ready to free a node, first I have to free the plate, the first name, and the last name, because those got mallocked, and then I can free the actual node itself. And to free the whole tree, you're going to just do a recursive traversal, and instead of printing the node, just call free. Call your own free node function, which frees those three fields, and then the node itself. So free an array. So when you do something like, car string bracket 125, right? I've said that this is effectively the same thing as car star str, and str equals malloc 125. The effect for your program from that point forward is basically the same, right? Except when this happens, the memory for this does not come from the memory heap, right? That pool of storage that malloc draws from. It will probably come from the stack. It comes from somewhere that does not have to be explicitly freed when you're done using it. And if you write a test program and make a character array like this, make a different character array like this, and look at the value of these pointers, you'll see they're pointing to fundamentally different locations in memory. Where this one points is in the heap, and that's storage that's not automatically reclaimed when you exit a function, for example. Whereas this is basically local to whatever function you're in. If you're in your main program, that's a function. It's stored on the stack probably. So you don't need to free these, and in fact you can't free these because they didn't come from the heap. But these you need to free because they did come from the heap. Where you declare that does not make any difference. If you put it in a .h file but include that in main like you were doing, including a .h is no different from just taking the contents of .h and typing it in place of saying include. So in your case, that string declaration was still inside the main program, or that main file. It might have been global outside of your actual main function, but it's declared at compile time, and that's the reason that it gets stored somewhere different from the heap. The heap is really for runtime allocation, so those need to be freed. Yeah, memory management with compilers and operating systems is a deep subject that I've only ventured around the edges of. Yeah, dynamic versus static, or runtime versus compile time, if you like. All right, cool. All right, let's talk about quicksort. So we went through bubble sort, insertion, selection sorts yesterday. Those were order n squared. Quicksort is going to be an order n log n sort algorithm. I urge you to pay attention, because if you look up in 5 minutes, you're going to be lost, because this is a lot of detail. Quicksort, we have a series of numbers, so I'm just going to make some random numbers. Apparently not totally random. All right, close enough. Here's the idea of quicksort. We start with one number that we call the pivot, and we just take the pivot to be the number at the end. And quicksort is a series of passes through your data. And the goal of our first pass is to put 16 somewhere in this array and arrange the other numbers so that everything to the left of 16 is smaller than 16 and everything to the right is bigger than 16. Okay, that's the goal of one pass. We're going to take this one number that we call the pivot, usually the last number in the array. We're going to rearrange things so that when we place the 16 somewhere in here, everything to the left is smaller, everything to the right is bigger. And if we do that, if we find that everything to the left of 16 is smaller and everything to the right is bigger, that means 16 is in its proper final spot when the whole sort finishes. So for example, I've got, when this thing is finally sorted, so let me cheat here and just kind of look ahead. When this is finally sorted, we should have an 11, a 12, sorry, we should have a 4, 11, 12, 13, 15, 16, 17, 19, 23. So when we're finally done sorting, the 16 should end up right here. And when we look at the sorted array, everything to the left will be smaller than 16, everything to the right will be bigger than 16. All right? Our goal in our first pass of quicksort is not to sort this stuff, not to sort that stuff, but to get 16 into this spot and to make sure all of these numbers are to the left and all of these numbers are to the right. All right, got the goal? Let's look at how we do this. So we make a pair of pointers. Our first pointer is going to begin with the first number. Our second pointer is going to begin with the last number. We don't compare the pivot. We're comparing things to the pivot, so we don't compare the pivot to itself. All right, we're going to start from the left. And remember, we want things on the left to be smaller than 16. So we look at 12. 12 is smaller than 16, so that's fine. Let's go on to the next number. 23 is bigger than 16. So we're going to stop here. And we're going to move to the arrow on the right. And we're going to say, on the right, we want things to be bigger than 16. Well, 19 is bigger than 16. That's fine. Let's move in towards the middle. 15 is smaller. That's a problem. Right? We want things to the right to be bigger than 16. We want things to the left to be smaller. So here's something that was bigger than 16. Here's something that's smaller than 16. Those are in the wrong order. So what do? We swap them. So once we swap them, we have a 12, a 15, 11, 17, 4, 13, the 23 came over here, the 19, the 16 is still the pivot. I'll put our arrows back in to remind us where we were, and now we continue. Alright, so we were at the 15, we move over to the 11. 11 is smaller than 16, that's fine. Continue, there's a 17. Oh, 17 is on the wrong side, it's bigger than 16. So we stop there, and we go back to the right side arrows. Okay, we had done a 23, let's move in one spot. Here's a 13. 13 is not bigger than 16. So again, we found a pair of numbers that are in the wrong spot relative to 16. We're going to swap those. and I'll redraw the new list. So the 13 came in place of the 17. 17 took the place of 13. 16 is still our pivot, and I'll redraw our arrows so we can see where we were. Alright, so I'm going to continue from the left again. I'm going to look at the 4. 4 is smaller than 16, that's fine. I'm going to move over one more spot, and I've hit my arrows from the other side. As soon as your arrows meet, you're done with this pass. And where those arrows meet, that's where the 16 should go. So now we're going to swap that collision point with the pivot. And here's our list at the end of this first pass. So the 16 comes in here, and the 17 goes off to the end. And I'm going to put a circle around that pivot that I just swapped in. Right? Now that 16, that's in what we, peeked ahead and saw. That's where it's supposed to end up. And everything over here is smaller than 16. Everything over here is bigger than 16. Okay? That's the essence of quicksort. We make a pass through the data, and at the end of that pass, this pivot should end up in the right spot in the array, and everything to the left should be smaller, everything to the right should be bigger. And the cool thing is, this one pass is order n. Yeah, you can read some history about this on Wikipedia, about the person who dreamed this up and made a bet with their advisor, I think, that this was a faster algorithm than the sort they were going to use. Alright, so why is this order n? Well, we start from each end and we move in, and we might come over and move in from this end and move in from this end, but at some point our arrows are going to meet, and that's going to happen after we've interrogated a total of n pieces of data, right? I'm not worried about plus or minus 1. And we might do some swaps along the way, right? But swapping is a fixed amount of time. It's 2 or 3 assignment statements, right? So this is basically, if you have n pieces of data, it's n operations to go through one pass. Now, our data is not sorted, right? 12, 15, 11, 13, 4, that's not sorted. 23, 19, 17, that's not sorted. But we know the 16 is in the right spot, so all we have to do now is sort this array and sort this array. And how do we sort these? Use quicksort. So it's a recursive algorithm. And we could write it something like this. This is going to be heavy pseudocode, so don't get tripped up by indices. Let's sort an array called data containing n elements. Okay, how do we do this? Make one pass. Find location for the pivot. And let's say the final location for the pivot is F, right? So that's where this number should go. All right. So, swap the pivot and data bracket F, and then quicksort data 1 through F minus 1, and then quicksort data F plus 1 to N. Alright, so that's quicksort. It's a kind of complex, or at least, you know, non-intuitive pass that moves, you know, a number we call the pivot into a correct spot and leaves things on the left and right, you know, all with the same sense relative to the pivot. So everything here is smaller, everything there is greater. And then we would call quicksort on this array, and we would call quicksort on this array. Well, quicksorting this will turn it into, you know, 4, 11, 12, 13, 15. There's our 16. Quicksorting this will turn it into 17, 19, 23. Bingo, your whole array is sorted. Right? There's your sorted data. And sorting those subarrays we just do with recursive calls.
So if we ran through this again, and we did quicksort data from the second one, f plus 1 to n, wouldn't the next line of that also include f minus 1 for the other side? So we would get 16 again?
So
Getting like doubles.
So the next call to quicksort would be on this array of data right here, 23, 19, 17. So we would say 23, 19, 17. So this would be our pivot. And we would start here, and that's in the wrong side. And so we'd come to the right, and that's on the correct side. And then we find our other arrows, so our arrows have collided. So this is where the 17 belongs. We swap, and now our data looks like 17, 19, 23. This is in the correct spot. And now we're going to call quicksort 2 more times, once on the left sublist, which is null, and once on the right sublist, which is 19 and 23. But when we quicksort, you know, this list, we're never dealing with 16. When we quicksort this list, we're never dealing with 16. So that's why I did 1 to f minus 1 and f plus 1 to n, assuming that the pivot went in location f. Does that make sense?
Yeah.
Okay. And you need a base case for this, right? You always need a base case with recursion. And a reasonable base case is if you only have one element in your array of data, just return. There's nothing to sort. So your one pass is order n, and you're going to call quicksort twice. And each of these is going to call quicksort twice, and each of those is going to call quicksort twice. But you're going to keep doing this until you call quicksort on an array of length 1. Now, if you start off with n pieces of data, and each of these calls to quicksort deals with an array half the size, this is going to take roughly log n of these recursive calls. And it actually turns out that, you know, even though we only have to go down log n times, right, our first pass, we're going to end up calling quicksort twice. Well, this call to quicksort is going to call quicksort twice, and this call to quicksort is going to call quicksort twice. So we're going to end up calling quicksort 4 times the next round of recursion. And the next round we would end up calling it 8 times. So back of the envelope calculation, this would look like n squared, but in fact each of these recursive calls to quicksort sorts a list roughly half the length of the original. And so if you work this out, this actually ends up being on average n log n, which is nice, a whole lot better than n squared. So 1,000,000 times more data, order n squared would be a trillion x increase in work. 1,000,000 times increase in data, n log n is like 6 million or something, or 20 million. Right, so pretty nominal, not quite linear order n, but pretty close to it. So that's a nice kind of ideal performance characteristic. but it can get bad. So worst case. And the worst case is kind of funny. Suppose your data starts off sorted. So we'll take our pivot over here. This is smaller, 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 and we're out of data, which means the 83 is in the correct spot. So now we have two subproblems. One will be to sort the null list on the right. The other will be to quicksort this list. So we call quicksort with a new subproblem, which is, hey, let's sort this. And we'll put the pivot at the right, and we'll start moving from the left, looking for things that are smaller. We get to the end, hey, the 67 happened to be in the right spot. Now we have to call quicksort on this list. And if your data is pretty close to sorted to begin with, each time you call quicksort, you're not actually splitting your list in half. Right? The goal is to cut this in half to get that log n behavior. But with sorted data, each time that you call quicksort recursively, the length of the array you're sorting goes down by 1. And so worst case, this becomes order n squared. Yeah, maybe n minus 1 squared or n times n plus 1 over 2 or something, but ballpark order n squared. Bubble sort, right? So how do you avoid that? Randomize your data before you sort it. Which is kind of weird, right? Like someone brings you, you know, a bunch of stuff and says, hey, I got most of this sorted, can you finish? And you say, sure, and first thing you do is throw it on the floor and jumble it all up, right? It will sort quicker if you do that, in general, if you randomize the data. So that's a strange quirk of quicksort. All right, questions about that? So play around with this. Make yourself an array of numbers and practice doing the quicksort algorithm, right? Pick any numbers you want and pick a pivot and just practice going in with the arrows. We're not going to code this, right? You might in other courses elsewhere. But you know, I might ask you on an exam to show me, you know, a few passes of quicksort. So make yourself some numbers. Go back to the videos, play around with this, figure out how one pass works, and then bring questions to class or office if it's not clear. So tomorrow we will look at merge sort, which is another recursive sort, and it's also n log n, but it's a little more straightforward to explain. It's actually something that we kind of do in everyday life. So we'll play with merge sort. And then we'll look at radix sort, and then we're going to talk about heaps and heap sort, and heaps are really fun. I wasn't planning to do comb sort, but if you want to post a reference to it, that would be cool. There's so many sorting algorithms out there, it's crazy. And I'm not very familiar with comb sort. All right, cool. I will see you tomorrow. Have a good afternoon. Looks like the sun is trying to come out, so I'm going outside. All right, have a good one. See you next time.